All right, we are looking at sequences this week. Well, actually, we looked at sequences last week. Series now. Oh man, can't seem to keep those two straight every once in a while. Sometimes I switch those words around. But like we talked about last week, a sequence is just a list of numbers, and a series is when we add those numbers all together. And that's the main difference between those. So we're just going to look at a few examples of that. You guys have worked with series before when we were starting in with our integrals and things like that, where we had to add up a bunch of infinite things. And so we're kind of a review here and just kind of, re-looking at that again. So it's a little bit of a review, nothing too major, should go fairly smoothly on this one. So like I mentioned, a sequence is just that list of numbers. So here, like you were working with last week, 1, 1/2, 1/4, 1/8, or however that list is generated. And then a series is saying we are going to add up all of those numbers together and see what we get. All right, so we've done this a little bit before, some terminology and things like that. We can have what's called a partial sum. And a partial sum is we're not adding up everything, but we're only adding part way. And we represent partial sums by putting a capital S for summation. And then in the subscript, we put however many pieces we want to add. So like S sub 1, we are just adding the first piece, 1. S sub 2, we are adding the first 2 pieces, 1 plus 2, and then 3 pieces, and so on for however far you want to do that. And you could add up each one. But that's what a partial sum is just adding up part way through. Nothing too major there. Just want to make sure we go over that. Some other terminology as well that tracks with the last few things you've been doing the last couple of weeks. Something that is convergent means that it has a discrete answer, means it has a numerical answer that you can get. Right? We can figure that out. So a convergent series is a series that when you add it up, you get a particular number at the end. Right? Something that is divergent means you get something that is non-discrete, meaning like it might be infinite or negative infinity. That would be a divergent series. So the same terminology we've been using for integrals and for sequences also apply for series as well. One way here to test for divergence, to test a series, is to check just the sequence, right? To ignore sort of the summation part and look at just the individual pieces of the sequence in there. So in here, what we would do is to test this to see, well, does this converge? Does it diverge? It's sometimes easier to test for divergence. And to test here for divergence on this one, what we would do is we would take a look at the limit as, let's go to n goes to infinity, right, of this big thing here. So I probably should have just grabbed the whole thing, but it won't take too long. So we would test the limit here, and you guys can probably see this thing here. You could use LHOP, would probably be the most efficient way here. We're going to get 2/6, which is 1/3. So here, this thing goes to 1/3. Yeah. So one way to test for divergence is to check the limit of this sequence, and we can see the sequence converges. The sequence converges, which means the series will diverge. And if we kind of think about that for a little bit, it makes sense why this thing would end up diverging, because the sequence goes to something that is non-zero, basically meaning like we're going to add up a bunch of numbers, and then eventually we're kind of get to a point where we're essentially taking one, like this goes to 1/3. So we're essentially going to be doing 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3. And that's always going to continue to get larger and larger and larger, right? So the series itself is going to go to infinity. Like this is just going to keep getting bigger and bigger by, just adding 1/3 at a time, right? Essentially, that's what's going to be happening. So we would say here the series diverges. Because if this becomes a non-zero number, right, if it's any number other than 0, you're essentially going to be adding that number forever and ever and ever. So it's constantly going to get bigger and bigger and bigger. So in this, a little bit careful, the sequence converges to 1/3, but the series then will diverge. Yeah, so it's a little bit, we got to keep track of those two things. Now, on the flip side of that, we do have to be a little bit careful. This is only a test for divergence. This test does not work for something to converge, okay, to see that the sequence or that a series converges. And we can still test this, right? So I put this example here, 1 over n, so basically being like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so on. That sequence actually converges. It converges to 0, right? We know that. Like the numbers are slowly getting smaller and smaller and smaller. But however, the summation of all of those pieces, 1 plus 1/2 plus 1/3 plus 1/4, actually diverges, right? That will be infinitely large, which is kind of a weird thing. And we'll take a little more look at that stuff in the next section in 8.3. So if you're wanting to see how that works, that's actually in 8.3. I'll show why that does not. But even though here the sequence converges to 0, that does not automatically mean that the series will add up to something, right? It's evidence that maybe it will, but we do have to actually try and figure that out, figure out what it's going to become. And so one way to figure out what a sequence is going, what a series is going to add up to, there are some different ways. You can try and come up with a formula to do that, but one way to do that is to check a geometric sequence to see if it's a geometric sequence. And you guys have probably seen this before in some algebra stuff, but a geometric sequence is something where you start with a number and then you're continually multiplying by another number to get the next piece, right? Now, obviously, if this is multiplying by something larger than 1 or smaller than -1, right? If it's something outside of that, obviously this is just going to keep growing and growing and growing, so therefore it will diverge. So I'm not going to go over that stuff. If the number is big, if the multiplier is bigger than 1, automatically it diverges. There's no point in doing that, right? It's just going to keep getting bigger and bigger. But if it's less than 1, this number is going to keep getting smaller and smaller and smaller. And we can actually figure out exactly what that series is going to become. So here's a little bit of a proof, a kind of pseudo proof of why this becomes that way. I'm just saying that S is our series or our summation. We're going to add up all the pieces. So here we would start with A, and then we'd multiply times R again, forever and ever and ever. So to basically take this, I could sort of step this up a bit by multiplying everything by R. Take this one times R, take this times R, take this times R, and make an entirely new series, right? It's related, but it is a little bit different. And then the idea would be we would subtract these two things, right? We would subtract these two. So what we'd end up with is we'd take this top one, which is just S, and we would subtract the S times R. And we would want to see, well, hey, I wonder what that is equal to. And if we take a look, when we subtract these two things, if we take this top one minus this bottom one, these two will end up canceling out, right? I mean, those two end up going away, and these two end up going away, and these two end up going away, and these two end up going away, and so does everything on down the line. The only thing that survives throughout here is A. That's it. It's the only thing that survives. So all of this stuff is equal to A, right? Which then we can very simply solve for capital S. That's what we wanted to know in the first place. So here we could factor out our S value out of there. We could say that's S times 1 minus R, and then we would just simply take this and divide it over here. And there is what that series converges to, right? Is that our, I guess I should capitalize it, but our sum is A over 1 minus R. And that is under the impression that R is, well, technically in between -1 and +1, right? but it's something smaller than 1, because if it's larger than 1, we can't actually do that. It will just simply diverge and we're done, right? This has to be something smaller than 1. So an example of that is one that we just kind of looked at here, or that was at the beginning, right? We have 1/2, 1/4, 1/8. This is a geometric series. We are constantly multiplying by 1/2. So in here, I would say, well, the sum then has to be equal to a over 1 minus r, which are a values, whatever we're starting with, 1, divided by 1 minus r value, the ratio, r for ratio, whatever that multiplier is, which is 1/2, which we could just go ahead and do here. 1 minus 1 over 2 ends up being 2, because you have 1 divided by 0.5. And so we know that this whole thing is going to add up to 2. Now, again, this summation will never actually get to 2 because we have to go infinitely far, but it's going to approach 2. That's kind of the way to think about it. This series will never become 2. It will just constantly get closer and closer and closer and closer to 2, right? If we were able to go infinitely far, we'd get to 2. And so what that leads me to is I'm going to show you guys the solution. Some of you guys were trying out that clone escape, which some of them, you were able to do, right? Some of them are possible. But actually, the last one, the level 4 question where you have 3 clones in there, is actually impossible. And I'm going to show you why that's impossible using this idea right here. The idea on their clone escape is what we're going to do is give each one of these grid or each one of these blocks a value, right? So if we start with our first corner, I'm going to give that one a value of 1, right? Very simply, we'll give that. And so every time a clone splits, it's sort of half of its own value before. So when it splits, it goes this way and this way. So that means this block is worth a half and this one's worth a half, right? Because we split that value in half. And then same thing here. Each of these two is worth only a fourth, right? And same here. This one splits into a fourth and a fourth. So every one of these values is worth only 1/4. And we can actually keep that going. Each one of these values is 1/8, right? All the way down here. The next one is 1/16, and so on, right? That's what this would be. And then 1/32. And we can keep going from there. 1/64. I'm just going to fill these in if you want to jump ahead, to where we've got that. Oh, that one's going to format a little bit weird, so we're just going to give her some room. All right, 1 over 1/28, and then 1 over 256. And you could keep going as well. But that's what basically all those are worth, infinitely far out. We could kind of keep going with this. But what we're going to do is look at what's the summation under each column, right? What's the summation under each one of these? So let's add a row below here. Add row, insert row below. And I'm just going to color all this stuff, I don't know, green for our, we're going to total all this stuff up. So under here, if we add up this column, look here, this is 1 plus a half plus a fourth plus an eighth plus a 16th. That's exactly what we were doing here. So if we add all that stuff up, we should get 2. If we add up this infinite column, this entire thing is 2, right? And then if we add up this infinite column, it's the same thing, but half the amount. So this is actually going to be worth 1. Or if you wanted to, you could say it's a half, right? We could put a half on the numerator divided by a half, which is 1. And then so on, right? This would be a fourth divided, on all those things, a fourth divided by a half, right? And so on, right? These are just going to also just be half of the previous one. And that way, what we'd want to do is get this thing to be 1 grand total in here, right? And the grand total would have to be all of this stuff, 2 plus 1 plus yada, 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 which this, again, is just another geometric sequence, right? A geometric sequence here, so we can use the idea of a geometric series, where we can take the first number, 2, divided by 1 minus the ratio, a half. So 2 divided by a half is 4, right? So the grand total in this case is 4, right? That's what that is. Now, if we take a look at this a little bit more, we'll find out that the 3 problem is not possible. Okay? It's not possible to do that. And the reason that that is if we look at where those red pieces are at, it's not going to work out, right? Let's make this a little bit bigger there. So if we look at where these red pieces are at, if you just put down one piece, the total is 1. You can, you'd have to move out and into spots where they would total up to 1 out here, which you could do, right? I mean, you could have a 1/4, 1/4, 1/4, and then maybe a couple eighths, and there these spaces would total up to whatever you started with. However, if you start with all 3 spaces, a half and 1 and a half, this has a total value of 2 to start with, which means all of the white space out here also totals up to 2, because remember, there's only a total of 4 points along this entire infinite grid. So if you start out with 2, all of this stuff out here adds up to 2 as well, but it's infinitely large, meaning you could never actually get to that point. So I understand that, maybe you guys tried that a little bit. That last one, that level 4, actually turns out is impossible to do unless you were able to play the game for an infinite amount of time, which just is not possible in our dimension. So just a little bit on there, that clone escape solution, if you tried level 4 and you were stuck on that for a little bit, it is impossible to do that. The other levels, though, are actually possible to get them to escape. The one that would be the hardest is where you have a 1 in the corner and then 1 more over here, because that's a total of 1 1/2, and that's the highest valued possible amount that would then be solvable. So for those of you that tried that, way to go. If you were trying this one here and you were thinking, man, this is really tough, yep, it sure is, because it's impossible. But that's it for today. Nothing too major. You guys have your assignment. It's listed under the description there. If you guys have any other questions, let me know.